So we're done with number 5. Okay, let's continue with number 6 and 7. Now for number 6, we have here an object is being pushed to the right on a rough surface with friction, or say on a rough floor, and accelerating to the right. Now how do we distinguish the forces involved in 5 and 6? So actually it's similar, except in terms of magnitude we take note of. So here in number 5, the object moves at constant speed. Meanwhile, in number 6, the object is accelerating to the right, meaning to say velocity changes. Okay, velocity varies. Now, meaning to say acceleration, so to the right, so along the horizontal, is constant. So for number 6, okay, so we have here constant. Let me just, so a sub x is a constant. So we have here constant. Okay. And then, so let's draw the object again, just like in number 5. So we have here also in number 5, the object is pulled by a rope. This time the object is being pushed. Okay. So for example, we have a block, still a block, a box, for example. Then it is on the floor. So it is being pushed. So if the object is being pushed, so for example here, so we have here, the object is being pushed. So we have a force. So let's label it as F sub pushed, or let's just call it F sub A, or force applied. Or, sige, F sub push na lang. And then, we have a rough surface. So meaning to say, there will be a sort of magnitude of friction, or force by friction. And since the object is moving, so this will be friction, so kinetic friction. Then the object is accelerating to the right. So net force is to the right, okay? And then aside from these two forces, what do you think could be the other forces acting on the box? So since this object or this box has mass, then we know that there is a force due to gravity acting on this object. So we have here weight, and then we have weight, and then we have the normal force, F sub n. Now, the object is not accelerating along the vertical axis. So we can say that the net force along the vertical axis is equal to 0. Okay. So if we were to take the sum of the forces along y, that will basically be the sum of the normal and the weight due to, or the force due to gravity. So that will be F sub n minus W. Then since it is only, so it is only mass that affects, no change in acceleration, this will be 0 equals F sub n minus mass times g. There are no other vertical forces affecting the normal and the weight. So again, F sub n for this situation is just equal to the product of the mass of the box times the gravitational acceleration. On the other hand, if we were to get the summation or the net force along the horizontal, so we have here sum of f of x equal to, since we have constant acceleration, that would be the mass of the object times acceleration along the x-axis. So this will be m times a sub x equals the force, so due to the applied force due to pushing the object. So take note, to the right is still positive, to the left is negative, minus some force due to friction, F sub k. Now, if we were to get the magnitude of the applied force, this will be applied force equals, that's the net force, okay, minus, plus the force due to friction, kinetic friction. Now, later on, when we encounter problems, so given already the magnitude, we'll see how the force by friction relates with the normal force. Okay, so here it is just sensible enough that since the magnitude of the force applied is greater than the force due to friction, so this is basically kinetic. Now here in number 5, since the object is also moving, that's why it's also considered kinetic friction. But for example, there was an applied force, but the object stays in place, and basically it is just static friction. Now, one example of static friction is that if an object is at an incline and it is not moving. For example, cars on roads or parked on roads, and they are stopped or parked there. So what keeps those cars from sliding down is basically the static friction, no? The friction between the tires and the concrete pavement. Okay, so those are just a few realistic examples of static friction. Okay, so let's proceed to number 7, our just the one of the last examples for this part. Okay, for now. Oh, sorry. Okay. Now, all we dealt with the previous examples are basically all vertical, horizontal. Okay. But what if, for example, our object, so box lang gyapon, okay, and we tied that object with a rope. So for example, so for number 7, a rope directed at an angle 30 degrees above the horizontal is used to pull an object to the right across a horizontal surface with friction at constant acceleration. Now, how are we going to represent this in a free body diagram? Okay, so this is 7. So we know that we have a box. Say for example, the same box, and then it is on the floor, on a rough floor, horizontal surface. Rough floor, for example. And then there is a rope tied to it at an angle. Okay. So particularly 30 degrees. So let me change color. And so this is said to be 30 degrees. Okay, now we're asked what could be the forces affecting this box. So we have here, since we have a rope, we know there is a tension force. Okay, we have a tension. This box has mass. We have force due to gravity. That's weight. Okay, this should be straight. And then the normal force. Now this time, this gives us a hint that normal force is not equal to mg anymore, because we will consider the vertical component of this tension force here. And lastly, since we have friction, So we have here a certain amount of force. Now the box is moving, so this will be kinetic friction. Okay. Now let's try to put our focus here first on this tension force. And we know this is a resultant. Okay. We can treat it as resultant. So we have here tension. And this is T. Okay, let me change color. So this is T. Sorry. And then it has a horizontal and a vertical component. Okay, and this is 30 degrees. Now, how do we relate T to find the expression for its vertical and horizontal components? Of course, this will make use of your trigonometric function. So we have here a right triangle, and we can use two functions to find the horizontal and vertical components of this tension force. So looking at this vertical component, we see that it is opposite. Okay, let me emphasize this, since a lot of you are still confused up to now how to relate vertical and horizontal components to the resultant vector. If you're looking to see or look for the function to relate the opposite side of a right triangle to the hypotenuse, what function are you going to use? Okay, let's recall we have SOHCAHTOA. SOHCAHTOA. We see that if your side is opposite to the angle with the relation to the hypotenuse, then that will be sine. Therefore, the vertical component of this tension force is equal to the resultant T sine theta, or T sine 30. Okay, so let's just use theta for now, which gives us another hint. Here, if the side you're referring to or the component is at the adjacent side of the angle being of concern, rather, so this will be cosine. Okay, so this horizontal component is equal to resultant T times cosine theta. So if we were to plug in the value of theta, so that would be T sine 30 degrees and T cosine 30 degrees. Alright, so let me rewrite this one. So this will be T sub y equals T sine 30 degrees and T sub x equals T cosine 30 degrees. Now let's proceed to finding the net forces acting on this box. So we have here, let's try to find the summation of forces along the vertical axis first. Now we know that the object is not accelerating vertically. So basically, a sub y is equal to 0. And then, summation of forces along the y-axis is equal to the sum of all vertical forces, or forces along the vertical. So we have here, up is positive, down is negative. We have F sub n plus another vertical or force along the vertical is the tension, okay, so T sub y minus weight. Or in other words, we can write this as, so since our acceleration is 0, so net force is equal to mass times acceleration, so times 0, so this will be 0 equals, 0 is equals 0 equals normal force plus, we know that the vertical component of the tension force is equal to the force T sine 30 degrees minus W. Now in this case, we can clearly see that normal force is not equal to mg. Okay, so we can rearrange and find normal force. F sub n is equal to the weight of the object minus T sine 30 degrees. Okay, so this is our relationship for this particular example for the x along the x-axis. Now let's find the net force along the y-axis. So we have here along x-axis. Okay, summation of forces of along x equal to, we know that a sub x is constant, so this will be mass times a sub x. Okay. If we look at the diagram, what are the horizontal forces acting upon the object? Alright, so we have here the force due to friction and the horizontal component of the force caused by tension. And we know that this force is equal to the tension force times cosine of the angle. So we can rewrite this one as the mass times acceleration along x equals T sub x minus force due to kinetic friction. Or in other words, this will be net force equal to T cosine 30 degrees minus kinetic friction. And this is how we see, or how we find, the magnitude of the net force along the horizontal. So this is the relationship. Okay, now how do we relate? Okay, how do we relate normal force and friction? Normally, they are expressed as the magnitude of the force due to friction is equal to the coefficient of friction times, so let me just write that, times the magnitude of the normal force. So for example, in this case, since it's kinetic friction, meaning to say the magnitude of force due to friction is equal to the coefficient of kinetic friction K times the magnitude of normal force, which means force due to kinetic friction is equal to mu sub K times this expression. That will be weight minus T sine theta, or 30 degrees. Okay. So that's how you relate force due to friction and the normal force. So if it were static friction, then this will be coefficient of static friction. So our discussion, so introductory, apologies, introductory discussion for FBD ends here. So I hope to see you when we'll be able to solve problems now involving these different forces. So the concepts we learned here, we're going to apply them. So butangan na ni natong numero. Okay? See you in the next discussion.